We welcome Professor Alison Noble to Durham today. Alison is the Technikos Professor of Biomedical Engineering at the University of Oxford. She was elected Fellow of the Royal Society in 2017, a Fellow of the Royal Academy of Engineering in 2008, and Fellow of the Institution of Engineering and Technology in 2001. She was appointed an OBE for services to science and engineering in 2013. She's also appointed Commander of the Order of the British Empire for services to engineering and biomedical imaging in the King's Birthday Honours List in 2023. This is in addition to her many other career accolades. Alison's academic journey began at the University of Oxford, where she earned a first-class honours in engineering science in 1986, followed by a DPhil in computer vision in 1989. Her early research papers addressed feature detection in images, with one of the earliest detailing how to identify corners in 2D shapes by mathematical proof alone. No artificial neural networks in sight. They would come later. I did read the paper. After completing her doctorate, she joined General Electric's Research and Development Centre in New York, where she developed her expertise in the industrial applications of imaging technologies. Her return to Oxford in 1995 marked the formation of her groundbreaking biomedical image analysis group. This has since grown to be the largest biomedical engineering activity in Oxford. In 2002, she became the youngest person and jointly the first woman to be appointed as Professor of Engineering Science at Oxford. Her leadership extended to directing the Oxford Institute of Biomedical Engineering and serving as Associate Head of the Mathematical, Physical and Life Sciences Division, where she championed interdisciplinary research and innovation. Her early work on shape detection has progressed into techniques for improving ultrasound imaging, cardiac magnetic resonance imaging, and later fetal brain analysis, with the latter two quite literally helping to save the hearts and minds as she pioneered methods to automate point-of-care diagnostics. She's also a co-founder, director and senior consultant to a laboratory spin-out Intelligent Ultrasound Limited, which became the clinical AI division of Intelligent Ultrasound plc, and gets a bit larger, which in turn was sold to GE Healthcare last year. At the core of Alison's work lies her revolutionary integration of machine learning with ultrasound imaging. By developing algorithms that identify anatomical structures and pathological features in real-time imaging data, her team has created assistive tools that can enhance clinical workflows while maintaining human oversight, an approach in terms of human-AI collaboration. And it's the focus of her UKRI Turing AI World Leader Researcher Fellowship. It is all too common these days to walk around the university and hear the words, "Can't you just do that with AI?" We've all heard it many times this week, I'm sure. Now we will hear from a true world leader in the field about whether we can and also perhaps whether we should. Over to you, Professor Noble.
Thank you very much. Thank you very much. That was a wonderful introduction. Thank you. And I thought I'd just start by saying my connection with Gareth Roberts. As you heard, I'm at Oxford, and Gareth was head of a college there, Wolfson College. And my connection with him was as a young faculty, female faculty, very young child, trying to juggle being able to have an academic job. At Oxford, there's a lot of tutorial work as well as running a research group. And I was struggling with this as a whole. And how Gareth fitted into that was that he working with other people created a new position for me at Wolfson College. Wolfson College is a graduate college, so I didn't have to then have so much teaching for undergraduates. And really, without him, I probably wouldn't be here today, because that created me the space to be able to have the time in the early evening, which otherwise I might have been lecturing or tutoring, being able to spend that with my family. So what I'm going to be talking about is, I'm going to start by talking a bit about AI and science. One of my roles that I have at the moment is at the Royal Society. I'm one of the 2 foreign secretaries there, but because of my interest in AI, I've been heavily involved with some of their science policy work. So I thought I'd start by talking a little bit about how AI is changing science, and then using that to then link it to my own work, where my own research over the last decade or so has also been very influenced by adopting particularly deep learning into my research, and how it's allowed us to really explore questions we've not been able to do before. So that's what I'm going to do if my computer now decides to work. So I think if people think about how AI is transforming science today, a lot of people would immediately say something like AlphaFold. That's the example. So there are these capabilities that are coming out that have been, some of them by big tech companies who've got AI and science groups, but of course there's lots going on elsewhere, particularly in universities. And these capabilities you could describe, and some people describe them as being, they're so changing science because they're allowing humans to be able to look at problems in a way we've not been able to do that before. For example, in AlphaFold, it's looking at protein structures. And some people might think it's magic, but it's not magic. It's been made available by a lot of scientists, first of all, those who've created very large data sets, and then those who've figured out how you build computational methods on top of that that allow, for example, you to look at protein structure prediction. And it's also then is communities working together that are actually now transforming and totally changing certain areas of science. Other things are through what's called foundation models, again, very much enabled in the case shown here by having access to weather forecasting data, and then being able to do simulations that have never been possible before and do them quickly. Also in areas such as chemistry, you're now starting to see materials discovery being performed by robots, very automated, much better than a technician who might work 5 to 7. You can get these experiments done 24/7 and maybe a lot faster. So certain areas that's good. There are, of course, other questions you might put into play about the accuracy of using any of these techniques as well. So we're really starting to see, just emerging in certain areas, new capabilities driven by big data, and then on top of that, computational. And even in other areas, which is more towards my own work, these capabilities go down to just tools that scientists can use. For example, myself coming from a computer vision background, the ability to delineate round objects, to be able to count things quickly, to be able to put labels on things very efficiently. That's a generic tool. People working in computational areas, again, code generation can be automated, so it can save you lots of time. And then I just picked up the last example, which is really trying to use LLMs, that's large language models, to go think about the whole process in science of going and looking at the literature in an area, suggesting questions you might look at, then deciding which questions you might look at, but then the design of experiments. You could get your robot doing your experiments. You could get the AI to write your paper. You could get your AI to review your paper. And if you start to think this way, you're like, what is left to the human? Something to reflect on, perhaps. But in some areas, that will come. Is it bad? Is it not necessarily? It's just how things are evolving. But we need to understand how science is changing. So last year, the Royal Society, and I chaired the working group for this, was looking more at this. It was looking at more is how is science changing? How is the scientific process changing? And how is the scientist changing? And trying to get a feel of where we are today. Of course, a report comes out like this. In some sense, things are moving so fast, it's out of date immediately. But it's important to try and take a snapshot of this. So, being the Royal Society, we like evidence. So we got evidence base for this. Involved interviewing people, having round tables. You can see some of the topics that were looked at, from reproducibility to certain areas where the impact of AI was starting to have some effects, such as climate science. It coincided with the UK AI Safety Summit. And so then we were looking a bit about how safe is it used to things like large language models? How can you trick large language models to support what you say? Which we know happens, but this, of course, is as dangerous in science as it is in anywhere else as well. And how will we detect this in future? So there's some real questions that scientists have to think about here. And we also commissioned some reports. And this is the quote I love, because I think it almost summarizes some of the things that we really have to think about as well, is that everybody, particularly in science, wants to be first. We want to be the one, we want to be visible, we want to be known. So they want to be, if you like, if you think about what's going on, they want to be part of that sparkly fountain, the bit at the surface. But if we're going to adopt AI in science, what really, really matters is thinking about that boring plumbing underneath. That means thinking about the infrastructures that we require, the people who are not at the forefront, behind. AI in science is becoming very much about teams working together. And so that means that people who are setting up need to think about things like infrastructures to be able to do this, as well as we need to rethink in science some aspects of rewards and recognition within the research ecosystem that's evolving around using AI in science. Do I have the answers? No. Does everybody need to think about this? Definitely yes, and we're all part of that. So within this report, there were then these areas that are highlighted as sort of recommendation areas that were also particularly aimed thinking about policy, but are also for everyone to think about. This is that we need to enhance access to AI infrastructures. And what we mean by that is every area of science needs to be looking at what infrastructure it needs to be able to use AI and work with the AI. And in fact, it has to also define what it means by AI, because we use the term to mean very different things, from things like deep learning through to large language models, which are very, very different. That's sort of text interaction versus analysis of the data. And AI is all very much about the data as well. So in your own area of science, how much do communities work together in sharing data? Or how will you ask questions that maybe every lab might have some data sets? These are things that the areas that are adopting AI quickly already have the data or happy to work together. Trust is a big point here. Trust in the quality of AI-based outputs. They're generally what we consider black boxes. So you've got to be really critical about looking at solutions with AI to make sure that methods are reproducible. And this also brings in how open can you be. People talk about open science, being able to publish your data, your methodology, so that other people can reproduce it. Some areas of science, that's easier. I work in healthcare. That's hard because we can't share our health data. So how do we be open? And how do we look at openness in a field like that? Safe and ethical probably doesn't need to persuade people that's important, but safety is partly in the context of science, in the sense other people might use your results. So are you being safe within the context of your area of science? And the final bullet is not anything final on the end. It's probably the most important, because this is all about people. It's supporting the changes in the workforce skills. So how do we get people educated to be able to use this new scientific family of tools, both effectively, but safely and trustworthy? So if you're interested in this area, I do encourage you to read this report. There's sort of a chapter for everyone. I'm not selling the report. It was put together by many, many people, and it'll maybe get you thinking about some of these areas. What I'm now going to do is move across slightly into towards my area. I work a lot in medical ultrasound imaging, and my area of interest for many years now has been pregnancy ultrasound, which is one of the big areas of application for ultrasound. Sometimes you can consider it's part of radiology, but it's also slightly different because it wouldn't be in a radiology department. But I thought this slide sort of nicely summarizes the people we work with as engineers developing these tools. We work with people in clinical medicine. So how is AI transforming radiology as a whole? And I've gathered some of these pictures over the last 8 or 9 years to just show you the sorts of things that they worry about when they think about AI. It's things, again, like changes in the workforce and skills. Early on, people worrying about robots taking away doctors' jobs. And you can see some of the pictures there from about 5, 6 years ago. Of course, that hasn't happened. We've moved on for that. But that's clearly what was an issue in the early days. Big thing that's very much active today is how do you develop human trust in using an AI tool? And in the context of medicine, this is not just the doctors trusting it, it's the patients trusting the fact that the doctors were using it. And you actually find, if there's few studies that have been done in this space, is that patients are a lot more receptive to adopting AI than some areas of medicine, because they want answers quickly. As long as they're told that you've used a tool, they're quite happy with that. But for them, it's having information if this will move them along the patient pathway. AI regulation, very important for medical devices. So there's been lots of talk about how you can introduce regulation for AI tools. Reporting standards, which again is important in any area of science. It's particularly driven by clinical medicine. Is what do you have to report in a paper for the paper to be published in a top journal? And there's a lot of discussion about this, and it's really helping raise the standards of reporting of AI methodology. And the final one that's quite unique, I think, to healthcare is the challenges of data sharing. And this is because you're dealing with human patient information. And we're moving, certainly in our country and in Europe, into moving from data sharing to data access. And I'll touch on that in a minute. That has implications for how we can work with AI. This slide, to me, sort of from last year, summarizes where I think radiology is. The real question here being, will AI replace radiologists, or will it just make them better than ever? And again, if you're a scientist, you should be thinking about this as well. And it comes down to how good an algorithm have to be to take over your job. And if you ask people that question, you're always going to get very different answers. Humans are wonderful at having their opinion and maybe not always agreeing with everybody else. So how do we come to conclusions about adoption of AI tools? And there was these quotes here, if you have an opportunity to look at them. The first person saying, they're both leaders in the field, they have very different personal perspectives on this. The first one saying, if they're good enough, we should be using them. That's ridiculous, we're not. And the second one saying, well, I don't know. If we're not quite sure, maybe we shouldn't, and we need to be a lot more careful about this. And being more cautious. And you're going to get this view as well. So the sort of state-of-art questions in my area, which I've put technologists need to think about, and the end users, people adopting technologies being people developing the AI tools, is there are some really fundamental questions that are only starting to be asked, such as, it's not just about accuracy, it's about, does an AI model always need to be as good as a human expert? The answer there is sometimes yes, sometimes no. Do we understand human skill at performing a task and hence have a fair reference for AI? Normally, you set the standard and you say, as long as it's good as me, I'll use it. Do we understand human skill, though? The answer is no. So that's, again, sometimes yes, sometimes no type answer. And then you've got to think, what do you want the AI to do? Is it an automation tool? Is it an assistant, an instructor, or a peer? These are all very different use cases, and we're starting to hear people think about this too. The first wave going through have definitely been automation. So the people I interact with are thinking about these sorts of questions. So I'm now going to tell you a little bit about how my field's been changing, and towards the end, how we're starting to think about some of those questions with our collaborators in medicine. So medical ultrasound has been around quite a long time. And for many, many years, it was driven in two ways. It was driven by medical physics, trying to get images looking nicer so that you could interpret what was in the image. And it was driven, and hence also, from a user point of view, clinical applications. And everyone here has certainly had one scan. In fact, your first selfie was probably you in mother's womb. So the first picture of you was an ultrasound image. And so it's fundamental to healthcare. And you can see at the top there, in terms of the electronics, there's been massive change in how devices appear. There used to be cart-based systems, you'd wheel them around. You now have ultrasound probes that you can plug into iPhones. So it's a very portable technology. And with that, the number of use cases has increased. And what's shown here, I like to show this, is this was in 2019, but the prediction of where the technology would be adopted. And you can see it's moving more into community care, people who are less skilled, over the purple parts, over the hump and down. What was driving this was not the electronics, it was integrating assistive tech built on deep learning into the devices to mean that it was easier to scan and easy to interpret what ultrasound was doing. And it's that space that my own research has been working. So what I'm going to be talking about is then how AI has been transforming this whole area of ultrasound. And I have that little star there to say, when I say AI, I mean deep learning based methods. That's only one type of AI, but it's just easier to use the general term. And that's how I described it. Ultrasound, I've always been fascinated by this. Of course, I'm biased because most of my career I've been working on it. But why I love it is it's the interaction of a human. You've got a piece of tech and you're exploring. It's a bit like a torch. And because it's a torch looking in the body, you're trying to discover things. You're trying to check things. And you're looking at this as acoustic patterns. Humans are bad at recognizing acoustic patterns. So this is why using something that's very good at pattern recognition just makes a natural sense to see if that can be the interface between the human and a decision. And that's what AI set out to do. Deep learning is there to recognize patterns. So what we've been trying to do is to look at how these techniques that are incredibly good at pattern recognition, how we can incorporate those to simplify ultrasound, and particularly overcome and work with this very complex hand-eye coordination that takes a long time to learn. Can we mean that an occasional user can pick up the probe and scan and make a decision? And it'd be absolutely transformational if we could do that. And you can see a scan there and just a schematic showing what's going on there. So there's two ways that we've looked at that. We've aimed at what we call a high-skilled setting. This is people who have been trained to do sonography. That's to be able to take the scans. And then the other setting is minimally trained, where you've just trained people to follow these sweep patterns. And you can see the patterns over mum's abdomen there. And so they're very, very different, because the first one is freehand scanning. That's the exploratory. Then the goal is to capture what's called standard planes. These are the diagnostic planes. And then the image analysis part is then just knows about standard planes, and you just be automating what you find in a standard plane if you captured it. If you then move to the other type of scan, it's now video. It's video sweeps. And you've got non-standard planes. So you're given a video, and then the question is, what's interesting in that video? Can we discover things in the video? In our case, related to the health of the pregnancy. So what I'm going to talk about, just a little bit about the minimally trained setting, how we've used deep learning to help us, and then move to the highly skilled. We've worked on the particular use cases we've had. There are 3 here, have all been ones that you'd place in the global health settings. This is where you do not have screening programs for mothers. Mother turns up any point in pregnancy and she's not feeling well. First thing you might want to do is you need to determine how many weeks pregnant she is. That's called gestational age estimation. And second of all, you want to figure out what's wrong to triage and maybe refer her to the hospital or tell her to come back, or whatever your question is. These 3 projects are all examples of this. We've had really the privilege in my group of working with three groups who are doing pregnancy cohort studies, where they were acquiring the ultrasound data, large data set. And when I say large data set, for example, in the gestational age, we're talking there were 6,000 women scanned at 5 points in pregnancy. So it's a very large data set, carefully crafted. And certainly what I've benefited on with my group is working through our clinical partners on being able to have access to high quality data of the problem, real shared interest. They want to be able to look at adoption of tools into, for example, rural areas. And we want to be able to understand how we develop those tools with people who don't have expertise in ultrasound. We have complementary expertise. Theirs in pregnancy, as in building assistive tools. And there's also been, what's been a lot of fun as well, and very important, is this capacity building of researchers who are interdisciplinary researchers who understand how to work together in this space. Of course, you need funding as well. That's something we can take out of the lecture. At the time, though, we did have some good funding in this space. So the first example that I'm going to talk about was a project with India. It's called Colopus. And this was based on this scanning in certain patterns over mum's tum. It was initiated with a group who were doing a large, a high-profile project in India called the Garbini study, which is looking at health in pregnancy in the India context. And we were working with them on what's called a GCRF project, where we were using some of the data. We were introducing our protocol and working with them on trying to develop some tools. These tools, for example, recognizing the position of the placenta and being able to recognize certain structures in these sweeps. This is what we call the Colopus protocol. And by taking all these sweeps, what you're effectively doing is having this coarse grid across mum's abdomen. That's the key idea. Fetus might move, but you're essentially, it's a simple way to scan over the whole area. And what our clinical colleagues showed that you could go, by using this type of scan, you could then do the basic checks that we're looking at how many fetuses, was the heart beating, looking at placental localization, which is important. If the placenta's low, it's a high-risk pregnancy, and also doing some basic biometry on these scans as well. So they developed and validated this protocol. And then we developed some tools. The example here is looking at that low-lying placenta, where the green is the placenta, the red dot is the edge of the placenta. There's a 2-centimeter circle drawn around that. And what you're interested in here is how low that edge of the circle gets. So it's quite a simple thing to be able to explain someone, when it gets too low, please flag that as a high-risk pregnancy. We developed this tool to do this, which is shown here. And what was interesting in terms of understanding the black box was, if you looked at the feature representation for when the method failed versus when it succeeded, it was to do with the shape of the placenta. So there was a way to also explain the behavior. What we also have done with this project, and the reason I mention this is to show how important interdisciplinary research is that our colleagues in India, together with one of my students who was working on the placenta algorithm, did a small study in India, going out into the community and asking, would they find this type of tool acceptable in practice? And particularly looking at the usability, in this case, it was asking 31 healthcare professionals. This was from North and South India. And they all thought that if they had a tool of this kind, they would use it, and that they perceived it would be useful for their risk stratification. But you can't stop by just asking just questions like that. You've got to think about the healthcare system as well. Would it be acceptable within a healthcare system? In this case, there were some, the negatives came out when you started to think about this, because there were the obvious ones like ultrasound device purchase and maintenance cost, who would do that in the settings that might be rural settings. But something unique to India is an act called the Preconception and Prenatal Diagnostic Techniques Act, which means that you're not allowed to use handheld ultrasound probes unless you've registered the scan. And so, and it's to do with fetal sex determination in India. So it actually means even if you could develop a tool like this, it would not be acceptable to take that into this particular environment. Second example is one of gestational age estimation, and I'll explain a little bit more about that. This came around almost by accident, really, because to deep learning, the deep learning started about 2012 as a time reference. There was a big study done, a paper published in 2012 that showed you could recognize objects better than a human on a data set called ImageNet. So this was happening around that period. That I was working with some clinical collaborators, and they asked me merely to act as the role as the data storage center for their big ultrasound study. So by accident, I got involved with this large study called Intergrowth. But then what we realized was that this was incredibly rich. It's 5,000 healthy pregnancies from 8 sites. It then built a bit to go beyond that, and you can see the sites around the world. And what was special about this data is that they scanned women every week in pregnancy, and you also had, it was balanced data. So the women would come back so that you really, rather than have a lot of data at one time point and then a big gap, you had it throughout pregnancy. So that meant that if we wanted to look at estimating gestational age from this data, we didn't have to worry about imbalance, which is often the case when you work with machine learning algorithms. So one of the clinicians said to us was, well, we always fit ellipses, and it's shown here, for example, you find a head, you'd fit an ellipse to it. From the ellipse, the parameters of the ellipse is a lookup table to how many weeks you're pregnant. So why are you making us measure biometry? If I look at an image, I think I can say how many weeks pregnant that woman is. So they said, can you build an AI algorithm then that would work directly on the image? Because this would mean that we'd no longer have to do the manual basis of biometry. So that's what we could, because we'd got this very large data set, which I say is always key here, we could look at developing an algorithm that could do that. In fact, it was a little bit off the shelf in terms of the machine learning at the time. What was special about this was the data we had. And so this was with what's called second and third trimester. We had 4,233 examples. It was from the 8 sites, 5 continents, and importantly, the ground truth of definition of a gestational estimate. And what we found with this, and I clearly won't go into the details here, is that if you estimate using machine learning, you get a mean absolute error of 3 days in the second trimester and 4.3 days in the third trimester. This turns out to be, this outperforms current manual-based assessment that humans would do. So this is what the algorithm's then done is it's, without doing biometry at all, it's learned the patterns in these images that will tell you how many weeks pregnant a woman is, particularly important in the third trimester, where you start, normally the humans find it more difficult to fit an ellipse. So it's a really, really exciting result. It's showing an example where computer can do better than human. So you go, that's great, it's accurate, but then you have the question, who will trust it? You've now got a black box, turns out a number, we've proven it's better, but who's going to use this in practice? So what you then have to do is go and do a human study to actually see what humans think about using an AI tool that's challenging clinical practice. And this is what one of my students, Angus Nicholson, he's actually did his undergrad at Durham, so there you go, there's a Durham link, and a clinical fellow. They performed this little study, which I'll describe at high level. So they first asked the experts they gave them an image and they had to say how many weeks pregnant they thought the woman was. Then you leave a period of time, then you give them the same image, but now you have the AI prediction, and they can use both bits of information for them to say how many weeks pregnant. I think it is. The third one was adding an explanation there, and the explanation in this case is putting a box around the part of the image, in this case if it's a brain, what part of the brain was important for the algorithm to make a decision that said it was so many weeks pregnant. So you have the 3 types of experiment you do. And it's randomized so that you try and make it so the human forgets what they did before. So what did we find with that? Well, what we found was that if you just gave the AI advice, the number 2 for this example, then the errors reduced. But if you add the explanation, it was slightly better, but it turned out not to be statistically significantly improvement. And then you think, oh, well, almost negative result, wasn't what we wanted, wasn't what people say, which is when you add explanations, humans trust a system. But then you go deeper into, and you also asked information about the humans doing the experiment and how much they trust using AI and why they made their decision, including related to trust and use. And you could see that they partitioned into different types of people, if you like. They've got different profiles on them. And you found that participants who found this way of adding an explanation helpful, they were the ones who improved. But the ones who never really got it, they stayed the same or got worse. And it's showing the importance here, not a general result from a little study, but the importance of training people in how to use the AI and understanding its strengths and weaknesses. And this is quite hard. And we're now at this point where we're deploying tools. We don't stop there. We've got to make sure that humans work with the tools properly, because otherwise they're all going to use them in different ways. So it's a fundamental thing. Very few papers out there, not an easy study to do. You involve humans, you have to get ethics approval, but it's so important, particularly important for trust in using tools. Moving to the highly skilled setting now, this is the one where we're saying human, pick up probe, explore, capture an image, quantify. If you look at the literature, most work is on that quantification. All the hard work of getting to something interesting has been done, and then computer scientists come along and say, I can measure that for you, which is sort of back to front. The human finds it difficult to get to the particular interesting thing. But the focus of the literature is very much on that. So if you actually look at the literature, the top, in my area, automating fetal biometry, lots of literature. It's based on detecting things, detect X, classify Y, measure Z type of approach. That you'll see tools out in clinical practice. Standard plane detection is when you've captured an image to start with and you check the image is of a high enough quality that it contains the information. And that's something humans do vary. They'll, oh, that image isn't good enough, I'll take it again, for example. But there are standards that people are supposed to do if they capture images. And it's that particular problem of checking planes that I worked on with my spin-out company. And this is just, what's happened with this is you've reached the point where that the AI is as good as humans at doing this task. In terms of what they call scan completeness, in pregnancy ultrasound, you have to get these 21 different views. So does the AI help you get those if you're supported with it? So as you capture an image, it puts it in a check, ticks it off in a checklist, so you're less likely to forget to take a particular scan. Image quality as well. You find humans vary in their acceptance of a quality of a scan. There are international guidelines on what should appear in the scan. So if the computer's like sitting behind you going, well, that's not that good, take it again, or that's okay, move on. It just helps people in their work. So it's that AI assistant. You can get to the point where the AI is as good as humans. It's many, many experiments to do that. But the other thing that I like from this example here, which is showing it working in practice, is using the manual capture now with the AI-assisted capture, which is the one when you've captured it, it does the checking. There's less movement of the hand, as you can see here. And what you'll see in a minute is that using the AI assistant, you finish earlier as well. So you've had that automation, but importantly, there we go, the person's gone off to have their cup of coffee there. Of course, it isn't an identical experiment, but that is the general thing you find. This load, what's called the ergonomic load of moving the hands is reduced. And this is really, really important. People who do these scans, it's their full-time professional job. Their careers can be shortened by the fact they have problems with their wrist. Next thing, interest of time, I think I'm all right for a little bit. The other thing that I've thought a lot about is you have this complex setup, is how do we describe what's going on while human interacts with mum scanning? Can we model that process? And can we determine what's hard? Because if we can determine what's hard, we can build the assistive tech to be able to support people and make it easier. So we had this idea to instrument the room, essentially. So an instrument the room is really trying to get into what the human does. And we put a gaze tracker on the ultrasound machine so we can see where people look on the screen. We have an IMU, which is a little accelerometer on the probe so we can see how it's moved. And for some of the data, we asked the sonographers to speak aloud about what they were doing, because I couldn't put any brain things on sonographer. They were doing their clinical job. I wanted to get inside their brain as to what they're doing and why. So we had some audio as well. So we're now capturing what I call the sonography experience now. And so we have this multimodal data. And for people who follow what's happening in deep learning, multimodal analysis is a big thing. And we have it's a unique data set that was captured by working with sonographers in a clinic. It's what they were really doing. It was set up this way so we wouldn't interfere with what they were doing. So we actually know what some of the challenges are. This allows you to do what I call sonography data science, which is we've now got captured many scans. It was 1,500 scans in total. They're about 30 minutes each. And then we can look at how long people spend on certain tasks. We can look at where they look. We can look at another example of looking at cognitive load is we can look at how their pupil diameter changes. And so when they have a hard task and people focus, the diameter of the pupil changes, just to get a feel for measuring what they're doing rather than let them tell us what was hard. We've also looked at clinical workflows. That coloured patterns in the middle is colour coding what anatomy a sonographer was looking at and when. And you can see that there are different colours in there. There are different patterns. A lot of them start, in this case, with the red, which is the brain. And we were interested in here is, are the differences between how experts scan or how people who are newly qualified scan? And the answer is more. Everyone has their personal style, but there are some differences as well. But we have a tool set to be able to look at things like that. And then you can start to combine these different modalities that I've talked about. So video and gaze, you can come up with the computer can predict where someone looks on average. Video and probe is how someone moves the probe on average. Video and audio, you can start to build dialogues and questions about images, which is also a very sort of topical area at the moment. But I'm going to just mention the first two. The reason you want to do the reason I wanted to look at multimodal is because if you ask sonographers where do they look, you can't really trust where they look. So I wanted to measure where they looked. And what you're seeing here, that little green dot, is where someone's looking. And if you translate that to what AI algorithm people like, that's giving you this great point that you want to focus the attention of the algorithm. Because if that's where a human looked, they don't care about everything else. For this particular task, where that little dot goes was the most important thing. So if you've got lots of data like this, you can actually predict through the computer where a human would look. So this is my one scary slide of lots of architectures. This is what people working in the field would do. They would design architectures like this. These are sums we've looked at as about predicting where someone or an expert will look. In practice, what you end up with is something like this. You end up with this heat blob. Those heat spots are where people on average look in this scan. And fortunately, they're the structures they are supposed to look at, which is reassuring. And that little green cross you're seeing is actually where this individual was looking. The actual heat map we put on afterwards, so we did that retrospectively. So you can see how they flick between the two, which is what you hope on this. So we have done a study. We haven't published it quite yet. It's sort of in preparation. Is looking to see if you had a tool that was predicting where sonographers look. Is this useful for guidance? And the conclusion actually is no. It's a component. It's useful for guiding, but you actually need to tell people how to move the probe and also how to apply pressure as well. But it's a very important cue that we use, and as part of a system to guide, it might be in systems of the future. Video and probe. we've looked at being a robot, which is the first example, where you predict how much you should move the probe. If you've got a standard plane, the end target, and you're over here, what's the rotation to be able to get, or translation to be able to get you to a location? If you're a robot, you would say it in degrees. That's probably not useful to a human. You say, rotate the probe 13.8 degrees. They might look at you and go, I'm not quite sure. So, but for robotics, that's fine. What's more useful to humans was the solution we developed for the other example, which is where you have an image of where you are, and you show in 3D space where you are on the model. So the human can see where they are in 3D space, and then they have an idea of how much they move visually. And that's a human factors issue as well. And finally, we put those two together of gaze prediction and probe movement to look at the first time, can you come up with a model that tells you how to move a probe and where to look in one go? And it's a really exciting piece of work because this is taking us towards being able to support people in being able to scan. And that's what this is essentially. I wanted to just end by saying what are some other things that people are looking at, including my own group. And I've called these sort of emerging technologies. I mentioned this at the beginning. It's really important in healthcare to think about federated analysis. Within the UK, for people who work in healthcare, they may know this, is many hospitals are moving from sharing data to being able to researchers having access to data. And this means that we now need algorithms that can work with distributed data rather than centralized data. It's also very important, and that to be able to think about that, the example I had working with collaborators in India, we can't exchange data. It's really always because it's difficult from a data governance point of view. But that shouldn't stop us from building models together. And so this area of federated analysis is what deals with that. And the simple way of thinking about federated analysis is you've got a central model, that's the server, which holds the global model. And then each of these nodes would be like a hospital or a research institute. They hold the data, and you send the global model to each site. You then refine the model at each site. Those local model parameters are then sent back, and then you combine them all into a new global model and iterate. And that's what federated analysis does. It protects the data, but it allows you to build models together. And then there are a variety of issues. This is what one of my students work. There are all sorts of things you have to think about, like data imbalance. Each of the sites will have different amounts of data in different volumes. Some will be annotated, some will not. Some will be in both those cases. There might be missing information. You might have hospitals or sites that have solved individual tasks, and you want a model that is the global model solves all those tasks. So how do you build something that could be a central super task, if you like, solver? And so all these things are a very active area of where researchers are thinking about the trade-offs that come with working in a federated world when it comes to data. As an AI assistant, this is what we published last year, this is where we've now taken the whole video that's been acquired in a clinic, and we've summarized it to the key points, the key frames, describing the measurements. And so we've done that compression. It's a bit like someone was sitting there and writing everything down as you went along. You want this automated so that you could review quickly at the end. And we're starting to get to the point we can develop technologies to do that. And the final example, which sort of for me personally is the area I'm most interested in now, is human AI collaboration. Today's technologies, the AI will give you an answer and there'll be uncertainty, but you take it or leave it. It's just there. Whereas what you want is to be able to share tasks with the AI, where if the easy cases, you could automate, accept the result from the automation, but the human deals with the harder cases. So this is now joint decision making. And there's a particular type or family of techniques called learning to defer, where the AI algorithm, if it's confident, it will do the analysis, otherwise it defers to the human. So that's sort of my summary then. It's an incredibly exciting area for my area. It's using large-scale data, deep learning. We're solving established problems with sort of fresh insight, but it's also allowing us to think about really pushing the boundaries on looking at problems we've not thought we could solve before. It's adapting ideas that are coming out of the AI literature, but for me, the real value here is it's truly interdisciplinary. It's about doing team science. And everything I've on my summary slide, you take out ultrasound image analysis, you insert your own area of science is probably applicable to your space as well. Thank you very much.
Thank you very much. Okay, thank you very much. This is now open for questions.
Yes. Good, right. Can you hear me? No? Okay, well, that's awesome. Okay. Hello, Alison, huge fan. I mean, I've never been more excited to come to a lecture in my life. Really, I have to admit, sorry. So right now, I'm currently, personally, on the year out studies work, and I'm working with Planetary Technologies, which you might know, working in machine learning and AI. We're focused on crime and climate change, big data analytics. And I've always been personally quite fond of applying my interests in biomedical engineering, which is where I want to specialize at the end of the day. But I've found it to be so challenging working because, I mean, until now, we haven't really had federated learning, and it's been very difficult for a person like myself to be able to have access to high-quality, modern medical data to be able to develop apply AI, and develop models, essentially. And so my first question would be, I mean, what would you say are the biggest challenges in both regulation and regulation to ensure that, sorry, I'm just going to start the question. So what are the biggest technical and regulatory challenges you reckon we face to employ federated learning across the medical sector and beyond? And second of all, what would you advise someone like myself, an undergraduate, who wants to specialise in this sort of area? Thank you.
All right. Well, there are two big questions there. On the regulatory front for federated, I'm not an expert on that, but I would think it would be the normal rules that apply. The main one would be the privacy side of federated that you've got to preserve. I guess my own interest is much more for research collaborations where the regulatory issue that you're talking about is not such a concern. If you allow a small amount of risk associated with data, sensitive data leakage, that places you in another category. Then within the, if you like, the safe zone of working in research, what we need to move towards is that we can work together. But I think if we can demonstrate the value of doing federated, then some of the questions you're talking about, how we can move to methodologies being used for clinical practice, which is what I think you mean, will be addressed as well.
Perfect.
So that was the first one. Your second one,
yes.
prompt on the second one, because can't remember it.
How would you encourage? Because I mean,
well, no, yeah.
Because I'm currently struggling to find relevant data sets to be able to.
Well, you have to find the right partners and the collaborators. I think if you yourself as an undergrad, you should find a place where you could do a PhD, for example, or you find a company who are working with the NHS Trust to be able to have access to data. There are these SDEs, and that is the way forward. I think it depends whether you're currently an academic mind and you'd like to explore methodologies further, or you're thinking about going to work in industry. There's a lot of interest, clearly, in industry as well.
Do you have any space in your research group by any chance then? Or?
We could discuss.
All right, I'll approach Lisa. All right, thanks.
Following that open interview, are there any further questions? Yes,
Reception.
Yeah, thank you very much for the fascinating talk. My question concerns more about trust in AI, and it particularly pertains in context of your talk to when you were talking about the gestational age estimates for everything. Typically, for example, if I was in a clinical setting in a hospital and I had a controversial historical review report, for example, they might come back to you with the initial doctor's opinion and the second opinion, for example. And this is quite common in a room of physicists, for example, at CERN when we built the whole thing with 2 experiments. that were completely independent in pupil and the analysis to come up with the data analysis, for example. I wonder how that could possibly improve the trust in AI here by building independent models that can both produce predictions that humans therefore have some more chance of trusting.
Okay, I think that's a very good question. I think that is a way forward, but a point I think I'd like to make here is the way I view the AI is to treat it as a human, right? So if you had two humans making a decision and they'd performed the experiments or built a model in two ways, and you were deciding what to do, how would you draw consensus? Because at the moment, there's too much of the conversation we have is AI versus human. But if you think about AI being like it's a team member, then people start to think differently. And this is also actually very important in terms of thinking about doing team science. If you've got the opportunity to bring AI in, the question I say to people is, what's the job description of that team member you want to bring on board? What skills does it need to have, or he or she, or whatever? What are you looking for, and how would you embrace their strengths and their weaknesses? So if you start to do that, I think you're starting to think more sensibly about what an AI tool and model will do. You'll find it more acceptable, and you'll probably find its strengths, just as you would bring in someone who doesn't have much experience to start with, thinks differently. How do you work with them? And of course, if you don't like them, you let go of the contract, right? Or you fire them. So it's just a way that I think people aren't thinking that they could think. Does that sort of answer?
A brief follow-up from that is, if you were in a clinical setting or as a clinician or a patient, from that, do you think you'd rather work with, so you mentioned about how you work out who was the right answer, and often in computer science, if you have two people, you can't decide if they disagree. If you have three, then you can easily decide. Would you rather be two people and one AI, or two AIs and one person?
You have to do the experiments. And in fact, you said you only need three. You don't. You sometimes need 5 or 7. So this is what these experiments and understanding, the more difficult, or a human thinks the task is difficult. First of all, maybe the AI doesn't think it's difficult because there's patterns in there that takes what we would call shortcuts that can solve a problem. Or if you really are using data from humans, it can be better than a human, but it might not be. But is that still useful? Is that like having someone who you can work with?
Thank you.
Roger.
Hi. Very good presentation. Thank you very much for the presentation. One of the things I'm interested in from what you said is there's a lot of discussion going into AI around computing power and technology, and massive investment going into investment in integration of computing power. So in your example of the human versus the AI analysis of an image, you were saying the AI one was quicker, and we talked about some coffee before afterwards. To what extent is the performance there limited by computing power? So is the computing power that's being deployed at a local level, or is it at a broader level where you're using large amounts of computing power elsewhere? And if you had access to significantly more computing power, could the performance of the AI be much faster? Is it computing power limited, or if not, what is it limited by? The performance versus the human performance.
So the answer to that is, in the area I work, we're not the ones that really struggle large language models. I don't do large language models, and they struggle because they have so many parameters you have to update at each step in simple terms. In the work we do, training and validating what you do is where you need the compute. At inference time, it's fine. You can also reduce the size of the models as well. And then you need to look at the trade-offs in performance. So I think it depends where you are in that space. If you said to my research group, could they have more compute because they could do more? Of course, they're going to say yes, because they could run their experiments faster. But there is an area now that's looking at more efficient compute as well. in AI. I think it depends what questions you're looking at, but in my area, I don't think it's the challenges with the large language models, the very, very, very big models. Does that answer your question?
Sure.
I'm making toys. And so all the training things that you've done so far, you've used an instrument that's been optimized for human use.
Yes.
And then you're letting the AI enhance it beyond that.
Yeah.
Is there quite a big question that says, is that actually the best data set that AI could operate on? So, you know, in that you have certain particular directions.
Yeah.
That's because that's the way a human interprets the three-dimensional model. It's actually one of the other huge things with very little gets talked about is, are we using essentially the best data sets from AI to then?
Well, I think that's a very good question. I think the answer is probably we're not. So for some of the work that I guess I touched on here is by doing video sweeps, you've moved away from convention, which is to go from images. And then there can be patterns in the video that actually squeeze out extra accuracy, but that's tweaking. The other work in ultrasound is going back to the actual signal. And there are people, I don't work in that space, but looking at more the acoustic reflections and maybe the Doppler shifts and seeing if there's information there. Then you're getting into, which I do think is incredibly exciting, is into imaging biomarkers, and you'd have to validate against. But that, I'm sure we will see more of.
Any further questions?
Thank you very much. I really enjoyed the presentation. It's very close to the area that I need it more. I have a question about the part that you described trust in AI, and actually you categorize people into two main categories who really trusted, wanted to be, were happy actually with the AI, so the results of using the AI explanation increase their performance and vice versa. I was wondering if this measurement was a kind of self-report, or did you really look into their performance by measuring, for example, how close are their measurements into what you were looking for? Or they explicitly said that they're not happy because of it?
It was a qualitative study. So, and there's a study designed for it. You ask them their views of AI before and their knowledge and use of AI before. You get them to do your experiment and then you ask afterwards. It's sort of a framework that qualitative researchers advise we use. So our findings are based on that. It's going to clearly be, it's a snapshot in time now of doing that particular task. I'm sure as people get more used to using tools, like in radiology, if you repeated the similar experiment, you would have a different view because people's views are changing. So I think it's important now to do those because without them, you don't know. But it's not a result that's going to stay with time because people have their own experiences as well.
Are there any further questions?
Thank you for the talk. I was wondering, with the preferred to human, are you afraid of any loss of human expertise as humans rely more and more on AI's opinions, especially for the simpler cases?
Yeah, that's another. You're coming up all the great questions. That is. Again, it's something people have to look at. How do you retain, what does the responsibility of the human when they are using a tool? And that's the pushback in medicine because they can be quite cautious in adopting technology. And if they don't know the answer to that one, it could be a safety and a risk. We're actually working now with the human factors people who work in that space to try and understand what needs to be put in AI technologies so that is not an issue. But it's very important that the humans don't switch off and just trust the AI in doing things. I think the reality of introduction of tools is if the introduction's done properly, you'll understand which areas it's safe to introduce and then ones where you need these extra safety mechanisms are put in place. But I haven't seen work that's really mapped that out, but it is very important.
Thank you. Do we understand the limitations of the method? So you said that about an error of a few days, for example, but can you predict beforehand cases where it might probably go wrong, or cases where you do not need to be aware of it? What we learn in understanding and improving?
So that particular, the methodology that I taught there has not been introduced into general clinical care. So what would need to be done is studies looking at what you're talking about. The work that has gone into clinical care, the regulators look at this, and they keep the human, they'd have to do the human study to show that the errors were not what was required of the property of that image to mean it was safe to be able to use this type of technique. You have to counter that a little bit. It's a very, very good question, but the counter of that is there are errors happening in practice as well by humans. So, but we don't know what they are. So how do we understand when is the right level? And it comes back to that slide I have of this, there was in radiology, the ones who said, look, this is ridiculous, we're not using tools, and someone else saying, hold on, if we don't fully understand them, we shouldn't adopt them. And so that is what regulation's there, is about them monitoring in a period of time. You check it's not making mistakes, and there should be this continuous monitoring, but that is not there in the introduction of tools. And the ones that are being trialled at the moment for things like X-ray screening, that is one of the issues with those, is that it's not really understood when they are safe to use that well. But there are ongoing studies looking at that now.
My apologies for questions just before we go to the point. I think what we discuss here is to a certain degree decision support system. And my feeling is in order to give meaningful decision support, you have at some point to cross a bridge and provide and quantify the certainty of, better said, the uncertainty with your diagnosis, with whatever kind of conclusion you come to based on your pattern matching. Now, I'm not aware that this is a trivial task by using an EPI system. They're really started telling you how certain they are, actually. And to a certain degree, I think what happens here is that we have medical practitioners who quite often, in my experience, are not very good in discussing their certainty or uncertainty in their diagnosis. We have these medical practitioners, and possibly the best in the world, to train systems to then inherit this level of certainty. And my suspicion is that if you want to make AI a really, that is a step forward instead of any call it an automated, or don't want to be disrespectful, an automated like-for-like replacement of an expert with an expert system. I think that we have to promote it to a system that can honestly report on certainty or lack of certainty when analyzing certain patterns, certain pictures, certain whatever, real-life things, before we give decision support in hospital life and death type of decisions. And I just want to put this out.
Yeah, no, I agree. Yep. Yeah. So that the last slide I had on learning to defer is trying to look exactly at that, because you can set the parameters on it, and that's where you allow the automated algorithm to make certain decisions, and otherwise the human sees everything. And so you can have a setting that allows you to work between the two. And it's about then trusting the way the AI works. The other thing is, you're talking very much about diagnostics as if it's replacing experts. The support one are things like where it doesn't matter so much, but there's a very high throughput of examples. that if errors are made, they will be picked up later. That is another area where AI can work very effectively. So it's not making the final decision, it's helping you with that sifting process. And there are examples in that space as well. But what I totally agree with you, these things have to be looked at. But as you can tell, I believe that there are big roles for some of this technology, provided they are validated and used in context, and the people who are working with them understand how to call them out when they don't work, but also understand how to use them effectively.
Time for one final question, here's one. Okay. No, I'll bring this to a conclusion. We've had a really fantastic talk today, and I think it's shown that it goes beyond what many of us are conceiving as artificial intelligence. It's simply, here's a program running. We've seen some fantastic examples of the power of artificial intelligence in medical systems in particular, but also the broader implications for our science going forward. I think what's been perhaps even more insightful, though, is the broader issues associated with this, which have been raised by Alison today. This is the human factors involved with this, and also what's been really nice to hear is there's a change where we really are moving from individuals to teams, and we are going to ultimately be part of teams as scientists. So I think we've had a fantastic, insightful, thought-provoking and ultimately inspiring Sir Gareth Roberts Lecture in 2025. So let's thank the speaker again. Thank you very much.